All right, so let's talk about angular position, okay? And the symbol that we use for that is theta. Okay, if an object's moving in a circular path, then it's more convenient to describe its position by its distance from the center of the circle, which is r, and its angle, theta, which is in radians, from the positive x-axis. Okay, so you can see that in the figure below. So we can see that this is the positive x-axis down here, and the angle that an object has from the positive x-axis, okay, we're denoting that by this theta angle over here, and the distance that the object is from the origin, that's r. Okay, by convention, an angle measured counterclockwise, all right, so a clock goes in this direction. This would be 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. All right, so that's clockwise. Counterclockwise, this is clockwise. Counterclockwise would be going in the opposite direction that a clock would go. All right, so that would be this direction. So by convention, counterclockwise is the positive direction. So this direction that's in the figure right now, that's the counterclockwise direction. That would be a positive theta. If our line was in this direction over here, that would be clockwise, so that would be a negative theta. All right. Okay. So it says, by convention, an angle measured counterclockwise, or we just write CCW for short, from the positive x-axis is defined as a positive angle, whereas an angle measured clockwise, or CW, from the positive x-axis is defined as a negative angle. Theta, the units for theta is the radians, okay? And 2 pi radians is equal to, oh no, that's a typo, so it should just say pi radians is equal to 180 degrees. All right, so 2 pi is 360, so if we were to go a full circle, that's 360 degrees, and that would be equivalent to 2 pi in radians. So this full angle from here going all the way around would be 2 pi rad, which would be the same thing as 360 degrees. Okay, if we were just to go half a circle, so that would be 180 degrees, equivalent to just pi rad. All right, so now let's talk about angular velocity. So angular velocity is omega, and an object that is moving with a circular path is moving with an angular velocity omega. Okay, so that symbol that you see that looks like a fancy W, that's the omega symbol. And the units for omega is in radians per second. Okay, so how many radians, so what angle is the object moving in per second? So that's the angular velocity. It describes the rate at which an angular position of a particle is changing as it moves in a circular path. An object that moves in a circular path at a constant speed would have a constant angular velocity, is said to be in uniform circular motion. Okay, so its angular velocity is constant, so that means it's moving at a certain angle per second, and it's a constant angle per second that it's moving in. So that's said to be in uniform circular motion. Okay, so its angular velocity is the same, and its speed is the same, but its velocity would be different because remember, velocity is a vector, and it includes both the magnitude, which would be the speed, and its direction. And since when something is moving in a circular path, its direction keeps changing. So the velocity over here is a certain value, but it's going, let's say, up, whereas at this point, the object is moving in a different direction. So even though the speed is constant, the direction keeps changing. So the angular velocity would be constant, the speed would be constant, but the velocity would not be constant. It would be changing because the direction keeps changing. Okay? All right, just like angular position, by convention, angular velocity is defined as positive if the object is moving in a counterclockwise direction, negative if it's moving in a clockwise direction. Okay, so that's the convention that we're using: clockwise, negative; counterclockwise, positive. Okay, then we get into angular acceleration. So an object that's moving in a circular path with a changing speed and therefore a changing angular velocity, a changing omega, is said to be in non-uniform circular motion. And the angular acceleration, which is measured in radians per second squared, is the rate at which the angular velocity omega changes. Okay, so to put that in another way, the angular acceleration is the change in angular velocity over time. Okay, so it's how fast is the angular velocity changing over time. If the object was in uniform circular motion, then that means its angular velocity is constant, so the change in angular velocity would be 0, which means that alpha, the angular acceleration, would be 0. Okay, so if omega is constant, alpha would be 0. Okay, but if omega is not constant, then alpha is the change in angular velocity. So omega is not constant. Alpha is the change in angular velocity over the change in time. Okay, so angular acceleration alpha, which is measured in radians per second squared, is the rate at which the angular velocity omega changes over time. By convention, again, angular acceleration is defined as positive if the angular velocity is increasing in the positive direction or decreasing in the negative direction. Okay, so if an object is getting faster and faster in the positive, which means counterclockwise direction, so if our omega initial, let's say, is 2 rads per second in the positive direction, and our omega final is 4 rads per second, then our change in omega, which would always be final minus initial, would be 4 minus 2, which is a positive value, 2 rads per second. Okay, if the object was moving in the counterclockwise in the clockwise direction, then that would mean that my omega initial is a negative value. Let's say it's negative 3 rads per second. And my omega final, let's say in this case, the omega is getting less negative. So let's say it's negative 1 rad per second. If I were to find the change in omega, it would still be omega final minus omega initial. So omega final is negative 1 minus omega initial, which is negative 3. Negative 1 minus negative 3 is like saying negative 1 plus 3, which is 2 rads per second. Notice it's positive. Okay, so these are the two situations where the change in omega would be a positive value. You're either in the positive direction, speeding up. So see, we went from 2 rads per second to 4 rads per second. Positive direction, speeding up, or we're traveling in the negative direction, clockwise, but we're slowing down. We're going from negative 3 rads per second to negative 1. We're becoming less negative. We're not going quite as fast. Okay, so that's what we're saying here. By convention, the angular acceleration is positive if the angular velocity is increasing in the positive direction or decreasing in the negative direction. All right, so now we're going to talk about conversion. So we've learned already all the angular the linear kinematic equations. We're going to convert those to the angular kinematic equations. So if an object is moving in a circular path with a known radius and the position, velocity, and acceleration are known, then we can get the angular position, velocity, and acceleration easily. Okay, so if you know the linear position, so this would be s, the velocity, v, and the acceleration, a, then we could easily get the angular position, okay, which was theta, the angular velocity, which is omega, and the angular acceleration, which is alpha. All right, just from a simple formula. So consider that an object that's moving in a circular path that has a radius r again, as shown below, if the object is at an angular position of theta, all right, so the angle from the positive x-axis to that object where that dot is theta. That's the angle. Its linear position would be defined as its distance traveled from the positive x-axis, which we would call s. So this distance over here, that's the distance that the object traveled. So we're calling that s. Okay, so that's the distance that we've used in the past. So what distance does the object travel if it traveled a distance of theta in radians and is at a position of r away from the origin? Okay, so we can calculate what this s value is. So question 1 is saying, determine a relationship between the following: the angular position, theta in radians, the radius of the circle r, and the linear position s. Okay, so how do we find a relationship for this? Well, if we had a full circle over here, and we wanted to know the s, so let's say we started off at this position and we traveled all the way around the circle, and then we're back to where we started, then this whole circumference of the circle would be our s, right? And what would be our angle in that case? So what's this angle when you travel the full circle? So the angle is, we said already, it's 2 pi radians. Remember, everything is going to be in radians here. Okay, it would be 360 degrees or 2 pi radians. All right, so now what's the relationship between s and the angle? Right, what's the relationship here? So we can think about our circumference equation. The circumference of a circle is 2 pi r, right? That's the circumference of a whole circle. So if this is a distance, if this has a radius of r, then our circumference would be 2 pi r. Well, where's this 2 pi coming from? This is our theta. Okay, our theta is our angle of our circle, which we said is 2 pi. If we had a segment of a circle, so let's say we're just looking at this piece of a circle, and it had a different angle. It's not the full 2 pi. It's not the full circle. It's just a segment of the circle. And this is still r. And we wanted to figure out what this s value is. Then it would just equal, the s value would just equal to theta times r. Okay, so the circumference of a full circle is 2 pi r. The s, which is just the distance of any portion of the circle, okay, the arc length, would be theta times r. Okay, so that's what this answer is for question 1a. S is equal to theta r. If I know the angle, I could figure out this arc length, as long as I know this r value. Okay, so now I can think about the same thing for if I wanted to figure out what the linear velocity is compared to the angular velocity. Okay, so how do I relate these two? It would be the same idea. So we have the linear velocity is equal to the angular velocity times r. Okay, all we're doing is we're multiplying the angular version of the kinematic variables times r to get our linear version of that variable. Okay, so same thing for the next equation. We want to find a, which would be alpha r. So in each case, we're just multiplying the angular version of a kinematic variable by r to get the linear version, a. All right, let's do the next question. So it says, a small steel roulette ball, I'm just going to fix this, should say question 2, rolls counterclockwise around the inside of a 30 centimeter diameter roulette wheel. The ball completes 3.2 revolutions in 1.2 seconds. What is the angular velocity of the ball? Okay, so let's write down everything we know. We have a 30 centimeter diameter roulette wheel. Okay, so that's the diameter of the wheel. What would the radius of the wheel be? It would be half of that, right? Because the diameter is the length from one end of the circle to the other, passing through the center of the circle. That's 30 centimeters. That's my diameter. My radius goes from the center of the circle to the edge of the circle, so it's half as much. That's my radius. So my radius would be 15 centimeters, but we should change that to meters. So I'm going to change that to meters by multiplying by a fraction. Centimeters, I want to get rid of it, so I'm going to put it in the denominator, change it to meters. 1 meter is 100 centimeters. So I'm doing 15 divided by 100, and I get 0.15 meters. So that's my radius. The ball completes 3.2 revolutions in 1.2 seconds. All right, so we can use that to figure out what our omega is. Our omega is the change in theta over the change in time. Okay, just like our velocity is the change in position over the change in time. It's the same thing. Okay, so now we're going to find out what our omega is. So I'm going to do that on the side here. So we have omega is equal to the change in position in angular position. So our change in theta. So we've completed 3.2 revolutions. So it's 3.2 revolutions in 1.2 seconds. Now revolutions is not the correct unit for omega. It should be radians per second. So we need to change our units. So we have revolutions per second. Now I'm going to get rid of revolutions. Since it's in the numerator right now, I'm going to put it into the denominator. And instead of revolutions, I'm going to change that to radians. 1 revolution means you're going around a full circle, which would be 2 pi radians. Okay, so I'm going to just type that onto my calculator. I have 3.2 over 1.2, and I'm timesing that by 2 pi. And I get 16 pi over 3. Now I could get the decimal value for this if I wanted to, and that would be fine. Or I could leave it as 16 pi over 3. Now if I'm going to use that answer in a later question, I should use the exact answer, 16 pi over 3. But if I want to just finalize this question, question 2a is asking what's the angular velocity, I should just figure out what that is as a decimal, since that's the final answer for part 2a. All right, so I'm getting approximately 16.75. And my units for that would be radians per second. Okay, you can see the units cancel out here, the revolutions, and I'm left with radians per second. All right, so in part 2b, it says, what's the linear velocity of the ball? Okay, so I'm looking at this equation up here. I want my linear velocity, which is v. I now know my omega, and I also know my r value, my radius. So I can use that formula, v equals omega r. My omega, I can use 16.75, but I should really include extra digits to be more accurate. So I'm just going to type 16 pi over 3 here. Times by my r value in meters is 0.15. I'm just typing this on my calculator. And I get 2.51 approximately. And the units for that would be meters per second. This is just our regular velocity. Okay, velocity is a vector, so we should include the direction. So I don't know the direction this is traveling in. It's a ball that's traveling counterclockwise around a circle. But in terms of linear velocity, I'm just going to say it's going forward. All right. All right, so now let's take a look at our kinematic equations. So we had 3 kinematic equations from before, and now we're going to figure out what the angular version of these kinematic equations are. Okay, so if we take a look at that first equation, SF equals S initial plus V initial delta T plus 1/2 A delta T squared. If I divide everything by R, what's going to happen? So I'm going to get SF divided by R, SI divided by R, VI divided by R, and A divided by R. Okay, so if we recap what we did in the last slide, we said S is equal to theta R, V is equal to omega R, and A is equal to alpha R. So if I were to divide everything by R, this first equation, I would take the R to the other side. I'm going to divide both sides by R, and I get S over R equals theta. So theta is equal to S over R. Same thing with the second equation. If I divide both sides by R, my R's cancel out. I get omega equals V over R. And same with my third equation. I'm dividing both sides by R. I get alpha is equal to A over R. Okay, so when I did my SF over R, what did that give us? S over R, that's theta. So since it has a subscript of F, I'm going to write that as theta F equals S initial over R, then that would be my theta initial, plus V initial over R, that's my omega initial, delta T plus 1/2 A over R, which is alpha, delta T squared. Okay, so that is my equation written out as an angular kinematic equation. So I'm going to write it in this table. So SF is now theta F equals S initial is theta initial plus V initial, which is omega initial, delta T plus 1/2 alpha delta T squared. Okay, and I can do the same thing for all three of the kinematic equations. My V final becomes omega final equals V initial, which would be omega initial, plus A, which is alpha delta T. So remember, I'm just dividing everything by R here, and that makes all of my linear variables turn into angular variables. And I can do it with the third equation just the same way. So V final squared is omega final squared. V initial squared is omega initial squared, plus 2 alpha SF is theta F minus S initial turns into theta initial. Okay, so by simply just dividing everything by R, this whole thing gets divided by R, then all my variables change. Okay, question 3. A small steel roulette ball rolls around the inside of a 45 centimeter diameter roulette wheel. Okay, so that's my diameter again. That's the distance from one side of the circle to the other side passing through the center. That's what my diameter is, 45 centimeters. So my radius would be half as much. So that's 22.5 centimeters, but we need to convert that to meters. So I'm going to put centimeters in the denominators, meters in the top, and I end up dividing by 100 because there's 100 centimeters in 1 meter. So I get that my radius is 0.225 meters. It is spun at 150 RPM, but it slows to 60 RPM. So my initial angular velocity is 150. RPM stands for revolutions per minute. So we just need to change the units around because omega should be in radians per second, not revolutions per minute. So let's multiply this out so that we get rid of revolutions and we change them to radians first. So we want to get rid of revolutions. It's right now in the numerator, so I'm going to put it in the denominator. Instead of revolutions, we want radians. 1 revolution means 1 complete full circle, which would be equivalent to 2 pi radians. Okay, so now my revolutions are gone. I need to change now my minutes into seconds because the correct units for omega is radians per second. So minutes right now is in the denominator. I'm going to put it in the numerator. And instead, I want seconds. 1 minute is equivalent to 60 seconds. Okay, so I can multiply all of this in. So I have 150 times 2 pi divided by 60, and I get 5 pi. All right, so your calculator might give you your answer with 5 and pi multiplied by each other to give you a decimal. Or if that's the case, you can just leave the pi out of your calculator and you would just end up with 5, and then you would just write down the pi because you know that there's a pi here. If you wanted to write the full number with the decimal, that's fine as well. Just enter extra digits so that your answer is not inaccurate. Okay, so the units for this then would be radians per second because our minutes cancel out as well. So I have radians per second. So that's my initial omega, and now I'm going to find my final omega, which it tells me it slows down to 60 revolutions per minute. So 60 revolutions per minute. Again, I need to change the units. It's the exact same thing I did before. So I want to get rid of revolutions. Instead, I want radians. So 2 pi radians is the same as 1 revolution, 1 complete circle. I want to get rid of minutes, so I put minutes in the numerator. Instead, I want seconds. 1 minute is 60 seconds. So I can multiply all of this. So I have 60 times 2 divided by 60, and I end up with 2. There's still a pi here, so I'm going to write 2 pi. And that would be in radians per second. Okay, so I know my R, my omega initial, my omega final, and now it tells me the amount of time. So my delta t, that's the amount of time that's gone by, is 5.0 seconds. And the question says, how many revolutions does the ball make during these 5 seconds? So it's asking how many times does the ball go around and around this circular path here? Okay, so what we're going to do is figure out what is the theta. Once we know theta, we can convert the units from radians into revolutions. So I'm just going to say theta is my question mark. Okay, I'm looking how many revolutions, but once we find theta, which is in radians, we can convert radians into revolutions. Okay, so what equation are we going to use? So if we take a look at the 3 kinematic equations, we can see that all of them have alpha in them. So we're not able to solve a question unless we know what alpha is. Okay, so we're looking at the angular kinematic equations. Just like the linear ones, they all have a in them, the acceleration. In the angular version, all of them have alpha. Okay, so we can't really solve this until we figure out what alpha is. So here we know omega final, omega initial, and delta t, so we can use equation number 2 to figure out what the alpha is. Okay, so here's equation number 2. We're going to use that equation. So let's write it out. Omega final equals omega initial plus alpha delta t. So let's use this equation to figure out alpha. I'm going to rearrange. So I have omega final minus omega initial equals alpha delta t. We'll divide both sides by alpha, and I get alpha. Sorry, I'm going to divide both sides by delta t, and I get alpha is equal to omega final minus omega initial over delta t. Okay, so let's figure out what that is. Omega final is the 2 pi radians per second minus omega initial, which is 5 pi radians per second, over delta t, which is 5 seconds. Okay, so what is our alpha there? I'm going to type this up on my calculator. So I have 5 pi minus, I have 2 pi minus 5 pi over 5. So I'd get negative 3 pi over 5, or I can just type it up and I get negative 1.885 radians per second squared. Okay, that's my alpha. Now I can use my alpha if I want to figure out what my theta is. Okay, so which theta is it that we're looking for? Is it our initial theta or our final theta? Well, really what it is our change in theta. We're looking for the distance that it's traveled as an angle. So what is the angular distance that it's traveled? So it's our delta theta. Delta theta is the same as saying theta final minus theta initial. Okay, or you could also say my theta initial, I'm going to say is 0. What's my theta final? That would be the same as the delta theta in that case. So now that I know what my alpha is, I can use a different equation to figure out what my delta theta is. So we can use equation 1. We also could have used equation 3. That would have worked as well. Okay, so let's go to equation 1. So our equation is theta final is equal to theta initial plus omega initial delta t plus 1/2 alpha delta t squared. If I bring my theta initial to the other side of the equal sign, I get theta final minus theta initial, which is delta theta. Okay, final minus initial means the change. So that's what this triangle is. Delta theta means the change in theta, which is final minus initial. So I'll just rewrite that equation. All right, so my delta theta is what I'm looking for. My omega initial, we said, was 5 pi. My delta t is 5 seconds, plus 1/2 alpha, which is negative 1.885 delta t squared. This is an alpha here. Delta t squared, which was 5 seconds squared. So what do we get here? I'm typing this on my calculator. And I get 54.98. Okay, so what would the units be? This is theta, that would be in radians. But the question's not asking for what the angle is in radians. It wants how many revolutions does the ball make. So we need to change this to be revolutions. Okay, so we're changing the units from radians to revolutions. So I'm going to put this in brackets. I want to get rid of radians, so I'll put radians in the denominator. Instead, I want revolutions. 1 revolution is 2 pi radians, right? If I go a complete circle, then that would be 2 pi radians. So 1 revolution is 1 complete circle. All right, so I'm just going to take my number and divide it by 2 pi. And I get 8.75. And the units for that would be rads. All right. So that's question 3. Okay, question 4. An old-fashioned single-play vinyl record rotates on a turntable at 45 RPM. So A, find the angular velocity, which the units should be radians per second. So we have 45 revolutions. RPM means revolutions per minute. And we're just changing the units to be radians per second. So that's angular velocity. I'm going to just call that omega. And so all I'm doing is changing the units. So instead of revolutions, I want to get rid of revolutions, so I put it in the denominator. Instead, I want radians. 1 revolution is 2 pi radians. I also need to get rid of minutes. So since minutes is in the denominator, I'm going to put minutes in the numerator. Instead of minutes, I want seconds. 1 minute is 60 seconds. And now I can just type this onto my calculator. I'm going to type in the actual value for pi so that I get a numerical answer without pi in there. So I have 45 times 2 pi times 1 and then divided by 60. And I get approximately 4.71. And that would be radians per second. So we can see revolutions cancels, minutes cancels, and I'm left with radians per second. All right, so that's A. And for part B, it says find the period of the motion. All right, period. What does period mean? So period is the time it takes to complete 1 revolution. Okay, so how much time does it take to complete 1 revolution? So that would be seconds per revolution. So right now we have the omega, the angular velocity, in radians per second, but we want the time, the seconds per revolution. So we can start off with seconds per radian and then change that to revolution. Okay, so my symbol for period is a capital T. Period is capital T. And instead of writing 4.71 radians per second, I'm going to write 4.71 radians over seconds that way. So I flipped it around. So my omega, if I take the inverse or the reciprocal of omega, I get 1 over omega, and the units become seconds over radians. Okay, so that's what I'm doing here. I'm just taking the reciprocal of omega, which flips my units around. Okay, so if I were to think, let's say I'm traveling 100 kilometers per hour, I could also say that in 1 hour, I travel 100 kilometers. Okay, so it's a similar idea. My velocity over here, 100 kilometers per hour, can be changed to 1 hour in 100 kilometers. So in 1 hour, I travel 100 kilometers. It's the same idea. I can flip it around. It's not called velocity anymore, but my units just flip upside down. So in this case, I'm looking for period, and I recognize that period has units that are very similar to omega, except they're flipped upside down. So all that I need to do is flip the units for the omega, and I get something similar to my period. So I have 1 second. It takes 1 second to complete 4.71 radians. But I don't want seconds per radian. I want to know how much time it takes to complete 1 revolution. So I need to get rid of radians. So I'm going to put radians in the numerator, and instead I want revolutions. 1 revolution is 2 pi radians. So if I type this on my calculator, I get that my period is 1 times 2 pi divided by 4.71, and that gives me approximately 1.33, and that would be seconds per revolution. So when I'm stating what my period is, I don't need to say per revolution, because the period definition is the time it takes to complete 1 revolution. So when the question says what is the period, you would say the period is 1.33 seconds. You wouldn't put per revolution in there. That's what the definition is. Okay, so if the question was like, how long does it take you to get to your house, you would say it takes me 5 hours. You wouldn't have to say it would take me 5 hours per trip. That's really the same idea. So period by definition is how much time in seconds it takes to complete 1 revolution. And so the answer is just 1.33 seconds. All right, but we took a look at the units for omega. We inverted them, or we took the reciprocal of it to make it the units upside down. So instead of radians per second, we want it to be flipped to be seconds per radian, and then we switched radians to be revolution, so that we'd have seconds per revolution, which is the definition of what a period is. All right, question number 5. The radius of the Earth's orbit around the sun is 1.5 times 10 to the 11 meters. If it takes 365 days for the Earth to complete 1 orbit around the sun, find the magnitude of the Earth's velocity. All right, so let's write down everything that we know. The radius of the Earth's orbit is 1.5 times 10 to the 11. So that's our radius. R is 1.5 times 10 to the 11 meters. It takes 365 days for the Earth to complete 1 orbit around the sun. Okay, so what can we use that for? What variable can that give us? That would be similar to our omega. It's just that the units are all off. So remember, omega is radians per second. In this case, we're completing 1 orbit. So 1 revolution in 365 days. So 1 revolution per 365 days. The units are not correct, but at least they're in the right direction. So we have revolutions per day. We need to change that to radians per second. So let's do that. So let's get rid of revolutions first. We'll put revolutions in the denominator, so it will cancel out. And instead we want radians in the numerator. So 1 revolution is the same as 2 pi radians. Now days. We don't want days, we want seconds. I don't know how many seconds are in a day, so I'm going to change days to hours first. So I'm going to write day on the numerator, and in the denominator, hours. 1 day is how many hours? 24 hours per day. I don't want hours though, I want seconds. Okay, so if you don't know how many hours are in a second, you can change hours to minutes first. So there's 60 minutes in an hour, and then you can change minutes to seconds. So there's also 60 seconds in a minute. Or we can say, I'm going to go directly from hours to seconds. In 1 hour, there's 3,600 seconds. Okay, 60 times 60. All right, so I can type all of this up on my calculator. I'm going to leave pi in my answer, so I'm not going to put that in. I have 1 revolution times 2 times 1, which doesn't do anything. And now I'm going to divide by the denominator numbers, 365, and also divide by 24, and also divide by 3,600. So I get this really, really small number. I have 1, and I'm going to leave this as a fraction. I have 1 pi, so I'll just write that as pi, over 15768,000. Okay, so that's the number that I get when I multiply all of these fractions by each other. And the units for that then would be the revolutions cancel, the days cancel, the hours cancel, and I'm left with radians per second. Okay, I want the Earth's velocity, and remember we had those 3 equations before. V, S, and A. S is equal to theta r, B is equal to omega r, and A is equal to alpha r. So I'm looking for this V equals omega r. So I have V equals omega r. My V is what I'm looking for. My omega is this value that I just wrote. So I'll leave it as this weird fraction like this. 15768. So I don't have all these decimals. And I'll multiply that by r. And my r is a big number, luckily, so it will make my number bigger. So I'm typing this on my calculator. And I get approximately 29884.9, and the units for that would be the units for velocity, meters per second. All right, so we went from radius, omega, which wasn't explicitly given to us in the question, but we were able to figure it out. It says it takes 365 days to complete 1 revolution. So we use that to find our omega, 1 revolution per 365 days. And then we just had to change the units from revolutions per day to radians per second. Okay, and then we just use that conversion equation to go from the angular velocity to the linear velocity using the radius that they gave us. All right, question number 6. You spin your 60 centimeter diameter bike wheel. All right, so right away I'm going to write down what the radius is. So my radius is half that amount, which would be 30 centimeters. And I'll change that into meters, so it'll be 0.3 meters. And notice that a pebble stuck on the tread outside of the wheel travels 3 revolutions every second. Okay, so this can help us figure out what the omega is. So my omega is 3 revolutions per second. 3 revolutions per second. The units are just not correct. I need to change revolutions to radians. So revolutions, I'm going to put in the denominator. Instead, I want radians. 1 revolution is 2 pi radians. So my omega is 3 times 2, which is 6 pi revolutions cancel, and I get radians per second. So now I know my r and my omega, and the question wants, what is the speed? So that's a v. Okay, so I can use that conversion equation again. V equals omega r. My omega is 6 pi, and my r is 0.3. Now I'm going to type it up with the pi and everything so I get my final answer as a decimal. Okay, so I have 6 pi times 0.3, and I have approximately 5.65 meters per second. All right, so my velocity is 5.65 meters per second. All right, so that was the final question. I hope all of that helped. Thanks a lot for watching. See you next time.